Imagine standing on the surface of another world. Red dust swirls around your boots. The sky above you glows salmon pink. In the distance, Olympus Mons, the largest volcano in the solar system, rises 3 times higher than Mount Everest. You are one of the first humans on Mars. But this isn't science fiction. This is the reality that awaits us in the next decade. And the question isn't if we'll go to Mars. It's who will be chosen for this unprecedented journey. Will you be among them? Today, we're diving deep into what it truly takes to become a Mars colonist. We'll explore the brutal selection process, the cutting-edge technology keeping you alive, and the 10 critical tasks you'll perform every single day on the red planet. This is your complete guide to surviving and thriving on Mars. Before you even set foot in a spacecraft, you'll face one of the most rigorous selection processes ever devised. NASA and SpaceX receive thousands of applications for every available position. The odds are tougher than getting into Harvard, multiplied by 100. So what exactly are they looking for? Let's break it down. First, the basics. You need a minimum of a master's degree in a STEM field. We're talking engineering, physics, biology, medicine, computer science. But here's the reality. Most successful candidates have doctorates. Why? Because on Mars, you can't just call a specialist. If something breaks, if someone gets sick, if a scientific opportunity appears, you need to handle it. Immediately. You'll also need at least 3 years of professional experience. For pilots, that means a minimum of 1,000 hours as a pilot in command on jet aircraft. But SpaceX is particularly interested in people with experience in extreme environments. Have you worked in Antarctica? The deep ocean? Remote deserts? High-altitude research stations? These experiences matter. They prove you can handle isolation, danger, and the unknown. The ideal candidate? Think of someone who's both a brilliant scientist and a wilderness survival expert. Someone who can perform surgery in the morning, repair a nuclear reactor in the afternoon, and still have the mental clarity to make life-or-death decisions under pressure. Now let's talk about your body. You need to be in exceptional physical condition, but not necessarily in the way you might think. Your blood pressure must be below 140/90. Your vision needs to be correctable to 20/20. You'll need perfect bone density. This is crucial because Mars's low gravity will leach calcium from your bones at a rate of 1 to 2% per month. Your height matters too. The spacecraft has physical constraints. You need to be between 5'2" and 6'3". If you're outside this range, you simply won't fit. But here's what most people don't realize. Astronaut training will push your body to its absolute limits. You'll spend hours underwater in a spacesuit, simulating zero-gravity repairs. You'll endure high-G centrifuge training that makes you feel like an elephant is sitting on your chest. You'll practice emergency procedures until they become muscle memory. And that's just the preparation on Earth. On Mars, the radiation alone will increase your cancer risk significantly. You'll be exposed to cosmic rays that would be blocked by Earth's magnetic field and thick atmosphere. Your immune system will weaken. Your muscles will atrophy despite exercise. Your spine will elongate in the lower gravity. This isn't a journey for the faint of heart or the weak of body. But here's the truth. Your mind matters more than your muscles. Imagine being trapped in a small habitat with the same 10 people for 2 to 3 years. No escape, no privacy, no fresh air. And if you have a conflict, you can't just walk away. You can't call a friend outside the base. You're stuck. The communication delay with Earth ranges from 4 to 24 minutes, depending on orbital positions. If you send a distress message, the fastest possible response is 8 minutes away. More likely, nearly an hour before anyone on Earth even knows you need help. NASA's psychological screening is intense. They'll put you in isolation chambers for weeks. They'll monitor how you handle stress, boredom, and interpersonal conflict. They're looking for people who are emotionally stable under extreme pressure, capable of self-motivation during months of routine, skilled at conflict resolution in confined spaces, and perhaps most importantly, comfortable with the idea that you might never return to Earth. Because that's the reality. The first Mars missions are likely one-way trips. The technology to return safely is still being developed. So you need to ask yourself, am I willing to die on Mars? If the answer is anything less than yes, you won't be selected. All right, you made it. You're on Mars. Congratulations. You're one of the first humans to set foot on another planet. Now the real work begins. Life on Mars isn't about planting flags and taking photos. It's about survival. Every single day, you and your crew will perform tasks that would seem impossible on Earth. Tasks that require expertise in multiple fields. Tasks where a single mistake could kill everyone. Let's walk through the 10 most critical responsibilities you'll have as a Mars colonist. Task number 1. Making the air you breathe. Mars's atmosphere is 95% carbon dioxide. It's also incredibly thin, less than 1% of Earth's atmospheric pressure. You cannot breathe it. Period. Your survival depends on MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. This device, about the size of a car battery, performs a miracle of chemistry. It sucks in Martian air, heats it to 800 degrees Celsius, and uses solid oxide electrolysis to split carbon dioxide molecules into oxygen and carbon monoxide. Currently, MOXIE produces about 10 grams of oxygen per hour. That's enough for one person to breathe for about 20 minutes. But a full-scale colony? You'll need machines 100 times larger, running 24/7. Your job is to monitor these systems constantly. Check the filters for dust contamination. Calibrate the temperature sensors. Ensure the catalysts aren't degrading. Because if oxygen production fails, you have hours to live, not days. NASA is also developing the Sabatier reaction system, which takes this further. It combines that carbon monoxide with hydrogen to produce methane, rocket fuel, and water. 2 critical resources from thin Martian air. The skills you need? Chemical engineering, high-temperature physics, and the ability to troubleshoot complex systems when replacement parts are millions of miles away. Future technology will include biological systems, photosynthetic bacteria that consume CO2 and produce oxygen naturally. Imagine vast underground caverns filled with cyanobacteria, creating a breathable atmosphere through the same process that transformed Earth's atmosphere billions of years ago. But that's years away. Right now, it's you, MOXIE, and chemistry keeping everyone alive. Task number 2. Finding and purifying water. Water on Mars exists, but it's locked away. Frozen in the polar ice caps, buried beneath the surface as permafrost, trapped in mineral structures in the rocks. Ground-penetrating radar has detected massive ice deposits just 1 to 2 meters below the surface in certain regions. Your job is to reach it. You'll deploy autonomous drilling robots that bore through rock-hard frozen soil at temperatures of -60 Celsius. These drills need to penetrate without contaminating the ice, because you'll be drinking this water, cooking with it, growing food in it, bathing in it. But here's the problem. Martian ice contains perchlorates. These are toxic chlorine compounds that make up about 0.5% of Martian soil. Ingest too much, and they'll destroy your thyroid, damage your kidneys, and disrupt your entire metabolism. So every liter of water must be purified. You'll use reverse osmosis membranes, distillation under low pressure, and chemical treatments. The system must achieve 98% water recycling, the same standard used on the International Space Station. A single human needs about 50 liters of water per day. That includes drinking, hygiene, and growing food. For a crew of 20, that's 1,000 liters daily. Over a year, 365,000 liters. And remember, resupply from Earth is impossible. If your water systems fail, you have weeks to fix them before dehydration kills you all. The technology SpaceX is developing includes subsurface thermal extraction, using nuclear heat to melt underground ice deposits and pump the water directly to storage tanks. These tanks will be heavily insulated and buried to prevent refreezing. Your skills? Hydrogeology, cryogenic engineering, chemistry, and the physical ability to operate drilling equipment in a bulky spacesuit. Task number 3. Growing your food. There's no pizza delivery on Mars, no grocery stores, no restaurants. If you want to eat, you grow it yourself. You'll be working in hydroponic and aeroponic farms. Plants grown without soil, their roots suspended in nutrient-rich water or mist. Why? Because Martian soil is toxic. It contains those same perchlorates we mentioned, plus heavy metals like cadmium and chromium. Your crops will include potatoes, high in calories and carbohydrates, lettuce and other leafy greens for vitamins, soybeans for protein, wheat for bread, tomatoes for morale. Yes, morale. Psychological studies show that fresh food dramatically improves mental health during long-term isolation. The smell of fresh basil, the taste of a real tomato. These things matter when you're 200 million kilometers from home. But growing plants on Mars presents unique challenges. Sunlight is 43% weaker than on Earth, so you'll use LED grow lights tuned to the exact wavelengths plants need for photosynthesis. These lights run constantly, consuming enormous amounts of power. The atmospheric pressure in your greenhouse modules must be carefully controlled, the temperature regulated, the humidity balanced. Too much moisture, and you get fungal infections. Too little, and plants wilt. You'll also need to deal with the lack of pollinators. No bees on Mars, so pollination happens manually or with small drones equipped with tiny brushes. Future technology includes genetically modified crops engineered to tolerate higher radiation, require less water, and grow faster. Scientists are also exploring insects for protein. Crickets and mealworms can be raised efficiently in small spaces and provide complete nutrition. Your role requires knowledge of botany, microbiology, agronomy, and genetics. You'll monitor pH levels, nutrient concentrations, and plant health. You'll prevent disease outbreaks. You'll optimize crop yields. Because if the food runs out, there's no backup plan. Task number 4. Shielding yourself from invisible death. Earth protects us in ways we rarely appreciate. Our planet's magnetic field deflects most cosmic radiation. Our thick atmosphere absorbs what gets through. On Earth, you receive about 3 millisieverts of radiation per year. On Mars, 250 millisieverts every year. That's more than 80 times Earth's natural background radiation. And that's just the baseline. Solar flares, violent eruptions on the sun's surface, can release radiation that would deliver a lethal dose in hours if you're caught outside. Mars has no magnetic field. Its atmosphere is 1% as dense as Earth's. You're essentially naked to the cosmos. Your job is to monitor radiation levels constantly. You'll have dosimeters on your suit, sensors throughout the base, and early warning systems watching the sun for dangerous activity. When a solar flare is detected, you'll have minutes to get everyone into the shelter. This might be a module buried under 2 to 3 meters of Martian soil. Regolith is an excellent radiation shield. Or it could be a specially designed room with water-filled walls. Water is one of the best radiation barriers we have. Long-term, you'll be constructing underground habitats. Lava tubes, natural tunnels formed by ancient volcanic activity, can be hundreds of meters wide and provide natural shielding. Some proposals suggest living entirely underground, with only surface installations for solar panels and landing pads. NASA is also researching electromagnetic shields, devices that generate magnetic fields to deflect charged particles, mimicking Earth's protective magnetosphere. This technology is still experimental but could revolutionize Mars habitation. SpaceX's Starship design includes using the ship's fuel tanks as temporary radiation shielding during the journey. Once on Mars, those tanks would be buried and repurposed as storage or living space. You need expertise in nuclear physics, construction engineering, and materials science. You need to understand radiation types, alpha, beta, gamma, neutron, and how different materials block each one. Because radiation is cumulative. Every day on Mars increases your cancer risk, your cataract risk, your risk of central nervous system damage. This is a sacrifice you make for the mission. Task number 5. Being your own doctor. Medical evacuation from Mars is impossible. If someone gets seriously injured or ill, they can't be airlifted to a hospital. There's no hospital closer than Earth, and that's 9 months away at best. You are the hospital. The mission will include at least one physician with extensive surgical training. But here's the reality. That doctor might be you. Even if you're primarily an engineer or scientist, you'll receive medical training equivalent to a military combat medic or remote field surgeon. Common medical scenarios on Mars include bone fractures from falls in low gravity, lacerations from sharp equipment, burns from chemical or thermal sources, and respiratory problems from inhaling Martian dust. That dust, by the way, is a serious hazard. Martian regolith particles are about 3 microns in diameter, small enough to penetrate deep into lung tissue. They're also highly oxidative and can damage cells on contact. Prolonged exposure could cause something similar to silicosis. Then there's the low gravity issue. Mars has 38% of Earth's gravity. Your bones will lose density at 1 to 2% per month. Your muscles will atrophy despite exercise. Your cardiovascular system will decondition. Astronauts on the International Space Station exercise 2 hours daily just to minimize muscle and bone loss. On Mars, you'll do the same. But it's not enough to completely prevent degeneration. You'll need to perform regular medical checks, bone density scans, cardiovascular assessments, vision tests, radiation exposure monitoring, psychological evaluations. And if someone needs surgery, you'll be doing it with whatever equipment you brought from Earth. No specialists, no backup. Just you, your training, and whatever you can improvise. Future medical technology for Mars includes 3D bioprinting of organs and tissues, robotic surgery systems guided by AI, telemedicine with Earth doctors advising via delayed communication, and cryogenic storage of blood and plasma. Scientists are also exploring gene therapy to strengthen bones, enhance muscle retention, and improve radiation resistance. Imagine editing your own genome to better survive Martian conditions. Your required skills span general medicine, surgery, dentistry, psychiatry, and emergency trauma care. You need steady hands, clear judgment under pressure, and the emotional strength to lose a patient when there's nothing more you can do. Task number 6. Keeping your artificial environment alive. The habitat modules on Mars are essentially fragile bubbles of survival in a hostile environment. Inside, breathable air, drinkable water, comfortable temperature. Outside, near vacuum, toxic atmosphere, extreme temperature swings. Your life support systems, officially called ECLSS, or Environmental Control and Life Support Systems, are complex networks of pumps, filters, sensors, and backup systems. Your job is to keep them running flawlessly. Temperature control is critical. Outside, Mars experiences wild temperature variations. At the equator, it might reach 20 Celsius during the day, then plummet to -73 Celsius at night. That's a swing of 93 degrees. Your habitat insulation must be exceptional. Heating systems will likely use nuclear power or stored solar energy. Every seal must be perfect, because heat loss in the thin Martian atmosphere is rapid. Pressure management is even more critical. Your habitat needs to maintain around 0.3 to 0.5 atmospheres. Enough to support human life, but not so much that the structure risks rupture. Even a microcrack could lead to catastrophic depressurization. You'll monitor pressure sensors, check door seals, and inspect the hull for micrometeorite damage. On Earth, our atmosphere burns up most space debris. On Mars, that protection doesn't exist. Carbon dioxide removal is another constant concern. Humans exhale CO2 with every breath. Without removal systems, it would accumulate to toxic levels within hours. You'll maintain lithium hydroxide scrubbers or molecular sieve systems that trap CO2 and release it back to the MOXIE units for oxygen production. Humidity control prevents condensation that could damage electronics or promote mold growth. Air circulation ensures even temperature and prevents pockets of stagnant, oxygen-depleted air. Every system has redundancy. Backup pumps, duplicate sensors, emergency protocols, because a single point of failure could mean death for everyone. NASA's technology includes AI-driven predictive maintenance systems that detect problems before they become critical. Machine learning algorithms analyze sensor data to predict component failures weeks in advance. 3D printing allows you to manufacture replacement parts on-site from raw materials. SpaceX is investing heavily in this technology because shipping spare parts from Earth is prohibitively expensive. You need skills in mechanical engineering, HVAC systems, electronics, and systems integration. You need to think several steps ahead, anticipate problems, and solve them before they become emergencies. Task number 7. Keeping the lights on. Everything on Mars runs on electricity. Life support, water pumping, food production, communications, heat, light, medical equipment, manufacturing. Lose power and you lose everything. Your primary power sources will be solar panels and nuclear reactors. Each has advantages and serious limitations. Solar power on Mars receives about 43% of the energy available on Earth. The sun is farther away, and the thin atmosphere still scatters some light. But the real problem? Dust. Martian dust storms can last weeks or even months. In 2018, a global dust storm covered the entire planet for months and killed the Opportunity rover. During such storms, solar power drops to nearly zero. Your daily task includes cleaning solar panels. This might be automated with brushes and air jets, but eventually you'll need to go out in your suit and manually clear them. It's tedious, dangerous work in a hostile environment. Nuclear power is more reliable. NASA's kilopower reactors are compact fission systems producing about 10 kilowatts each. They're designed to run for 10 to 15 years without refueling. A single kilopower reactor could support a small outpost. A full colony would need dozens, providing hundreds of kilowatts of continuous power. Your job includes monitoring reactor temperature, checking radiation shielding, managing control rods, and ensuring coolant systems function properly. This requires constant vigilance. Nuclear accidents on Mars would be catastrophic. Battery storage is crucial for balancing power supply and demand. Next-generation lithium-ion or graphene-based batteries will store excess solar energy for use during night or storms. You'll manage the entire colony's power grid, prioritizing critical systems during shortages, balancing loads to prevent circuit overload, and coordinating scheduled shutdowns of non-essential equipment during emergencies. Future technology includes small modular fusion reactors. Fusion produces enormous energy with minimal radioactive waste. The challenge is making it work reliably in Mars's conditions. But if successful, fusion could provide effectively unlimited power. Skills required: electrical engineering, nuclear physics, power grid management, and the ability to make life or death decisions about resource allocation when power is scarce. Task number 8. Unlocking Mars's secrets. Remember, you're not just surviving on Mars. You're there to answer fundamental questions about the universe and our place in it. The biggest question: did life ever exist on Mars? 3.5 billion years ago, Mars was radically different. It had liquid water lakes and rivers, a thicker atmosphere, possibly even rain, conditions that might have supported microbial life. Your mission includes searching for biosignatures, chemical or physical evidence of past or present life. You'll drill into ancient lakebeds like Jezero Crater, where NASA's Perseverance rover has already identified clay minerals that form in the presence of water. You'll analyze soil samples for organic molecules, study rock formations for fossilized microbial mats, investigate mysterious seasonal methane spikes in the atmosphere. Methane can be produced by geological processes, but also by living organisms. Geological research is equally important. Mars has the largest volcano in the solar system, Olympus Mons, standing 21 kilometers high. The longest canyon, Valles Marineris, stretches over 4,000 kilometers and reaches 7 kilometers deep. Understanding Martian geology helps us understand planetary formation throughout the universe. It reveals Mars's volcanic history, its climate evolution, and the processes that transformed it from a potentially habitable world to the frozen desert we see today. You'll deploy seismometers to study Marsquakes and determine the planet's internal structure. Is the core solid or liquid? How thick is the crust? These answers inform our understanding of rocky planet evolution. Long-term research includes atmospheric studies. Why did Mars lose its thick atmosphere? Was it solar wind stripping away unprotected gas after the magnetic field collapsed? Can we reverse this process? Your tools include mass spectrometers for isotope analysis, Raman spectroscopy for mineral identification, autonomous rovers that explore dozens of kilometers while you control them remotely, and orbital satellites providing geological mapping. Future technology might include deep drilling to access subsurface liquid water if it exists, or deploying submarine drones in underground lakes. Skills needed: geology, chemistry, biology, astrophysics, and the patience to conduct careful, methodical science even when every instinct screams at you to focus solely on survival. Because the knowledge you gain might determine whether humanity has a future beyond Earth. Task number 9. Building the future, one module at a time. The initial Mars base will be small, a handful of modules providing barely enough space for the crew. But the plan is expansion, permanent settlement, a growing colony that will eventually be self-sufficient. That means construction, constant, ongoing construction. You'll use 3D printing technology to create structures from Martian regolith. Special printers use microwaves or lasers to sinter, partially melt, the soil into solid, rock-like material. These printers can build walls, floors, and radiation shielding without importing materials from Earth. The process is called contour crafting. A robotic printer follows programmed designs, depositing layer after layer of material. Within days, you can construct a small habitat module. But 3D printing is just the beginning. You'll also excavate underground spaces. Lava tubes, natural tunnels formed by ancient volcanic flows, are perfect for habitation. Some are over 100 meters in diameter and kilometers long. Excavating these spaces requires robotic equipment. Autonomous bulldozers, drilling machines, and excavators operated remotely or by suited humans. The work is slow and dangerous. You'll construct landing pads for incoming spacecraft. These need to be level, stable, and free of dust that rocket exhaust could kick up into a dangerous cloud. SpaceX's Starship produces immense thrust, and landing on unprepared ground could create a crater and damage the ship. Radiation shielding for surface structures requires covering them with 2 to 3 meters of regolith. This is heavy, manual labor even in low gravity. You'll also build greenhouses with transparent sections for natural light, storage facilities for equipment and supplies, manufacturing workshops for maintaining and creating tools, and communication arrays to maintain contact with Earth and orbital satellites. Future plans include massive inflatable structures with rigid outer shells. These can be packed small for transport, then expanded and covered with regolith once deployed. Material science is advancing rapidly. Regolith-based concrete, called Martian concrete, can be stronger than traditional concrete while using only local resources. Your skills, construction engineering, robotics, 3D modeling and CAD software, material science and project management to coordinate complex multi-phase building projects. Because every new module, every expanded section, makes the colony more resilient and brings permanent settlement one step closer. Task number 10. Manufacturing your ticket home. Here's a reality that might surprise you. The first Mars missions probably won't bring enough fuel for the return trip. There's a better solution. Make it on Mars. SpaceX's Starship runs on methane and oxygen. Both can be manufactured from Martian resources using the chemistry we discussed earlier. The Sabatier reaction combines carbon dioxide from the Martian atmosphere with hydrogen, extracted by electrolyzing water, to produce methane and water. The equation is simple. CO2 plus 4H2, CH4 plus 2H2O. The water produced gets recycled back through electrolysis to make more hydrogen and oxygen. The oxygen serves double duty. It's breathable air and rocket oxidizer. To launch one Starship from Mars back to Earth requires approximately 30 tons of methane and oxygen. Manufacturing this much takes months of continuous chemical processing. Your job is to oversee the entire fuel production facility. You'll monitor reaction temperatures. The Sabatier reaction requires nickel or ruthenium catalysts at specific temperatures. You'll manage hydrogen electrolysis cells, compress and store the methane and oxygen as cryogenic liquids at -160 Celsius, and test fuel purity to ensure it meets specifications for rocket engines. Cryogenic storage is challenging. Even with excellent insulation, some fuel will boil off over time. You need to account for this loss and produce extra. The facility runs largely autonomously, but constant monitoring is essential. A leak could be catastrophic, not just losing precious fuel, but potentially causing explosions or asphyxiation. SpaceX envisions fully automated fuel production plants operating before the first humans even arrive. Robots would land, set up the equipment, and begin manufacturing fuel. By the time astronauts arrive, their return fuel would already be waiting. This approach, called in situ resource utilization, or ISRU, is fundamental to making Mars missions economically viable. Launching fuel from Earth requires enormous rockets. Manufacturing it on Mars using local resources costs a fraction as much. Future technology includes advanced catalyst systems that increase efficiency, solar-powered electrolysis requiring less nuclear power, and autonomous quality control with AI systems managing the entire process. Your required expertise: chemical engineering, cryogenics, industrial chemistry, and process control systems. Because this fuel represents hope. Hope that this isn't a one-way trip. Hope that you might someday see Earth again. So there you have it. 10 critical tasks that will define your life on Mars. 10 roles that require expertise in dozens of fields. 10 responsibilities where failure means death. But here's what makes it worth it. You won't just be surviving on Mars. You'll be building the foundation for a new branch of human civilization. A civilization that will grow, evolve, and eventually spread across the solar system. NASA's planning missions for the 2030s. SpaceX aims for the late 2020s. Within your lifetime, there could be a permanent human presence on Mars. Within a century, there might be 1 million people living there. Cities under domes, underground networks spanning thousands of kilometers, industries mining rare metals, universities conducting research impossible on Earth. And it all starts with pioneers like you, people willing to risk everything for a chance to stand on another world and say, "We made it. We're here, and we're not leaving." The question isn't whether humanity will colonize Mars. The question is, will you be part of making it happen?